Alright, good morning everybody. My name is Hamidisepehr. Today I'm a 5th semester PhD student. I'm working under supervision of Dr. Sam. Today I'm going to talk about the study for my PhD dissertation about estimating soil moisture using reflectance-based remote sensing. My advisory committee are Dr. Michael Sama, Dr. Vendros, Dr. Mantras, and Dr. Ivorak. So I'm from Iran, Middle East, so we can see where it is located, and about 6,600 miles from Ratictance. And like you can compare the size of the United States with the Iran, it's about 1/6 of the US. It's not that small. Well, I wanted to show you a couple of landscapes in our country. So you're very welcome to visit. You're gonna have fun, but anyway, you're gonna have some issues with your friends out. These pictures are from my family about 2 years ago before I came here, and that's after my graduation in 2012 for bachelor. And this is the picture I got like last year from California with my sister and my brother-in-law. Alright, enough about today's seminar. I'm going to talk about the result introduction, about the remote sensing, and also some like the moisture estimation in the agriculture. And specifically, I'm going to talk about 4 different objectives. So I'm going to go to the details, each one of them individually. So, during the recent decade, we had a great development in the nutrition and irrigation management practices. So it has resulted in a substantial increase in the crop yield, but on the other hand, it put a large burden on the global water resources. And there were some efforts that have been made to manage the water resources more efficiently. So, for example, using the variable rate technology. So, traditionally, water was applied at a constant rate, regardless of the actual needs of the field. But using the variable rate technology, we can minimize the amount of wasted water during the irrigation. And the zone delineation is a convenient method to limit the number of possible treatments. So in the field for the prescription maps, and also using the color mapping, we can visualize the difference between different areas in terms of their water status. The ground-based measurement is the primary method for obtaining some information about the drought status of the field. And typically, water potential and water content, there are 2 main ways to get some idea about the water status in the field. So the watermark granulometric sensor is a very common sensor. It measures the water potential. Water potential is basically the pressure which is needed to extract water from the soil particles, and the water content is simply the amount of water which is available in the soil profile. And using this curve, water retention curve, then they can be related. So, but the downside for the ground-based measurement, so is that we cannot use it for the larger scale fields, and also we cannot get a very high resolution data set. Remote sensing in agriculture has been considered as a hot topic and important topic since early 1990s. So traditionally, remote sensing was included temperature, microwave, and reflectance-based methods. And also there were several indices that were created to estimate particular parameters in the field. For example, NDVI is probably the most successful of the adoption of the remote sensing in agriculture. So it measures the crop figure, and because the crop figure is correlated with too many other parameters in the field, so we can get a better idea about the whole field. And the traditional deployments of the remote sensing would be the satellite, conventional aircraft, and also ground-based sensors, which are limited by their cost, spatial and temporal resolution. And for higher resolution method, so we can optimize the amount of input, actually reduce the amount of input and have the same amount of output. So, and it basically typically involves a combination of the visible near infrared or thermal infrared sensing technology. challenges like in the remote sensing in agriculture. So they are corresponded to the traditional deployments like satellite and the conventional aircrafts. The first one is the absorption of the light due to atmospheric moisture, and the second one is the soil contribution to the reflectance spectra, because most of the applications, the visual target is the crop canopy and not the soil. And the soil is considered as a noise. But there is a relatively new tool, unmanned aerial systems. So they are pretty cost-effective compared to the conventional aircrafts and the satellites, and also it can provide a high-resolution data set. And the recent advances in the spectrometer development have led to more portable spectrometers, which are very suitable for the UAS deployments. And for processing the spectral data, so as I said, it's very common to use index-based method. So they're gonna pick a couple of wavelengths that have the highest capability in estimating a particular parameter in the field. But the newer method is the machine learning algorithm. So using them, we don't need to ignore the whole wave range. So we can keep all of them and we can estimate different parameters in the field instead of having only one index. So the ability to quantify the moisture variability will improve the early detection of the water stress before any physiological and economic damage has occurred, and it will contribute to identify the zones in which the water is depleted faster than the other zones. So the main objective would be to develop some tools and methods to remotely sense the moisture variability in the field. The first specific objective would be to instrument some portable spectrometers and integrate into an UAS for autonomous data collection. And the biggest step would be to calibrate the data acquisition system based on the ambient light and the integration time. The second objective is to determine the feasibility of the low-cost index-based multispectral reflectance sensing based on the direct measurement of the bare soil and crop residue. The third one would be to apply machine learning algorithm to the full spectral data set to both lab data and the field data. So for moisture prediction. And the last one it would be to test the hypothesis that this reflectance spectra is correlated with the moisture content of the soil at field conditions and different ambient conditions. So in the first objective, we use two sets of the spectrometers, and each set has near infrared, visible, and UV, and each set is designated for either reflectance or radiance measurement. So you can see in this simple plot, the ground set is measured the ambient light, and we put it on the ground, and the UAS spectrometer we put it on the UAV and it measures the reflected light. So whenever I say the radiance, so it means it's the intensity of the sunlight, and the reflectance would be the reflected light from our target. And two Raspberry Pi microcontroller used for data acquisition as a data acquisition system, and we have a Python programming to set up the GPS, to pair the reflectance and radiance, to update the integration time. So we're gonna go to the details later on. And also we have this enclosure to easily integrate into a UAV and carry it over. There are different ways to trigger the measurements on these spectrometers. The default method is the Wi-Fi connection, so it's not a practical way in the larger scales. So we need to log into a web server. So for the larger scale, we cannot go with the UAV wherever it goes. So, but the push button, there's a push button method. So for example, when you want an exact measurement from a specific point, we go to that point, just take a measurement. But the main method for taking measurement from the UAS So it would be using the PWM signal. So it's intended to define a path on the autopilot and with a series of the waypoints. So the drone goes to these waypoints and stops at each of these points. So and when it arrives to that point, so it indicates. So we need to take a measurement, and it updates the PWM signal, and it sends it to the Raspberry Pi. But before that, because the Raspberry Pi can only read the digital input, we need a converter to convert the PWM to the digital input interface. So, and the last way would be the automatic cycle. So we're not going to wait for any signal. We take measurements every few seconds. In this slide, I'm trying to simplify the Raspberry Pi programming on the both ground station and the UIS unit. In the left part, both of them are the same. So the Raspberry Pi needs to be connected to the internet to have a correct time. And because we are not connected to the internet in the field, and we cannot be, we are using the GPS device, and we are trying to update the clock on the Raspberry Pi every few seconds, so we can be accurate enough. On the right part, so on the UIS unit, as I said, we're going to wait for a signal. It can be from the autopilot or a push button. We record the data, and we store the whole data in a file. We have a file naming based on the current time, so we can track it easier for post-processing. Finally, we're going to update the integration time for the next measurement. And for a ground station, so it's the same thing, but the only difference is that we're not going to wait for an input. So we just take measurements every few seconds. So the calibration of the system is a main challenge for this objective. So when we are measuring the intensity of the lights, so in different time of the day, so it would be different. So for example, if we take measurement early in the morning, it would be different from when we do it in the afternoon. And even we don't change the target, but we get different results. So we are trying to compensate the effect of the ambient light. So in the first step, we obtain the sun radiance and reflectance spectrum. We apply some correcting coefficients to the radiance values. So I'm going to visualize that in the next slide. And the next step would be the correcting the reference reflectance values based on the updated radiance. And we use this calibration target. So we are using different colors, so we can cover different types of soils. And also, we are assuming these targets are solid and their characteristics don't change during by the passage of the time. So we are assuming we need to have a spectral, a unique spectral for different time. We don't want it to be changed. So as I said, in this slide, so you can see, for example, there are tons of the data. We got this data from the eclipse the last month. So you can see this happened when the totality happened. We have the lowest intensity, and for example, when it was the partial eclipse, we had the higher intensity. So when the eclipse was totally finished, so we had the highest intensity. So as you can see, we don't change the target, and we should have exactly the same spectra, but we don't before the calibration. It's a raw data. And after we calibrated the radiance, so you see the variability is much lower. And if we consider, for example, just one of these wavelengths, for example 700, the variability is too high, but here, most of the variability has been removed. And it's going to be the same thing for the raw reflectance values. So because we are not changing the target, we should have exactly the same profile. But because we are changing the ambient light, we're not going to have that unless we calibrate our system. So you can see the density of these profiles are very high, around the average. And we have some outliers. So, but if I wanna show it in the histogram, so then you can see for example, for a wavelength 1000 nanometer, so it from the same target and same wavelengths, we are getting different intensity, and the probability is very evenly distributed. But it's not the ideal case. The ideal case is this one, and after calibrated, 90% we are sure that we are getting the same spectrum during the different times during the eclipse. So the same thing in different wavelengths. I mean, it happens in all wavelengths. And the next step in the calibration would be to calibrate against the integration time. So the idea, what's intended is to have the maximum intensity and at the same without any saturation. So we have a maximum intensity because if we have an integration time close to this line, it means we have the higher sensitivity, but we don't want it to be saturated. So we initialize the integration time, and after taking measurements, we check that, we check the difference, and we update the integration time to be closer to this maximum intensity. So when it is cloudy, we automatically update the integration time. It's like a closed loop control system, so we update it frequently. The second objective is to determine the feasibility of a low-cost index-based multispectral remote sensing from the direct measurements of the soil, bare soil, and the crop residue. 7 moisture levels are chosen. We use the silicon soil and wheat residue stock. So these two materials are the potential background when you're observing some row crops like soybean and corn. And these two lab spectrometers, they use the visible and near infrared. The effective range is between 400 and 1700. And backscatter reflectance probe was used to transmit the light from the spectrometer to the sample surface, and the reflected light from the sample surface back to the spectrometer. So to be consistent, we need a consistent method to minimize the variability of our sampling because of the height of the probe. So we use this test picture. It has 3 main components: the sample holder, outer probe mount, and inner probe mount. So the sample holder is for centering the sample underneath the probe. Outer probe mount is for it has rested directly on the sample surface, and the inner probe mount is for setting the height of the probe. And OceanView software was used to configure the spectrometers and also data logging. And the reflectance value was normalized using this equation. Like M is the raw measurement intensity from the target. The C0 is the background when the light source is blocked, and the C1 is the reference intensity. Like with calibration target is provided by the spectrometers manufacturer, and for different wavelengths we can have a normalized reflectance value. As you can see, before calibration, before we calibrate our values, so for the reference and background we have huge variability, and when we calibrate that, so when we don't have any light, we get 0, and we get 100 when we are using the reference light. So because we got lots of data, we need to plan ahead how to process our data. So I use this Filename schema. So it includes the height number, replication number, and the sample number. So using the MATLAB script, so we have all the text files, and which we can average between different replications, and finally we ended up with this Excel file. It has in the header, it has all the information we need for post-processing. And in this slide, so I plotted the reflectance value against the wavelength. So for the different moisture levels. So as you can see, for the higher wavelengths, for the longer wavelengths, we have higher reflectance values, and the drier samples reflected more light. But the difference between these two is the plots are very close to each other here, so it means probably other than moisture, there is another significant factor that affects on the reflectance. and it could be the height. So we can see later on the height is a significant factor in the Stalk residue. So we need to, like in the index space, we need to pick a couple of wavelengths that have the highest capability for predicting the moisture. So to do that, we created all the possible pair of wavelengths. So for example, I'm trying to visualize wavelengths number 1 by 2, 1 by 3, 1 by 4. So we keep going 2 by 3, 2 by 3, 2 by 4, and finally in the general form we're going to have something like that, and the index will be normalized using these two reflectance values. It will be a value between -1 and +1. So to make a decision on which index works the best for us, it has the highest accuracy, we considered 3 different parameters. The R square of the linear regression between the index and the moisture value, and also the slope of this linear regression. So when we have higher slope, it means the sensitivity of the index is higher, and also the RMSE, the amount of error that we have in our index. For the Bersol, as you can see inside the red rectangle, so it has the highest R square and also highest slope. So that's the global optimum point for us. But in the residual Stalk, because it has a different structure, we don't have a global optimum, but around the exact, and each point here represents a pair of wavelengths. So we have several of those. But the local optimum here in the residual Stalk happen at the same global optimum for the Bersol. When we pick one of those points inside the rectangle, so we saw this, like the variability for index is very low for the Bersol, so it worked pretty well in our index. The index is 1300 and 1500, and the same index works for residual Stalk, but the variability is much higher for different moisture levels. As I said, it could be for like a structure of the material, and also because the water probably is not distributed evenly during the whole sample. And when we do the statistical analysis on these two, Bersol and this Stalk residue, the moisture is the only parameter which is significant for the Bersol, but both height and moisture are significant factors with the Stalk residue. The third objective is modeling using machine learning. So I used 21 different machine learning algorithms, including decision trees and support vector machines. So it's a general assumption. We need to divide our data set to three sub data sets. So in the machine learning, we have training data set, 70% of our whole data set. So in this data set, we are trying to automatically adjust the weights of the different variables. So while the training is finished, and the validation data set, it verifies if any increase in the accuracy in the training data set will yield to an increase in the validation data set or not. And if it's not the case, so it stops the training, so it avoids the overfitting. And the testing data set is for to test the predictive power of our model. And the input variable here in this machine will be the wavelengths, different wavelengths, and the response variable will be the soil water content. So in this slide, I'm trying to visualize how it works. So a learning algorithm tries to mimic how the human brain learns by recognizing some patterns and rules in the data set. So by recognizing these patterns and rules, so it can make decision on some unseen samples. So it can be programmed. So it doesn't need to be programmed. It can learn it from previous experiences. So as you can see, we have n different samples in the training part, and in the prediction part, based on the experiences, we can make a decision on the new sample. And in this slide, I'm trying to show the difference between the objective-2 index-based method and objective-3, the machine learning algorithm. In the index-based method, we have n reflectance value, but we only pick 2 of them, because otherwise, if we pick more than 2, it's going to be computationally very expensive, and we only include 2 of these. But in the machine learning, we include all the reflectance values, and we're going to come up with a comprehensive equation. So it includes all the different wavelengths. The point is that in the machine learning, we don't need because there are about 2,000 different, over 2,000 different wavelengths. Many of them are highly correlated to each other, and we don't need to consider them individually. So we can combine them together and then compress the data set, avoid overfitting, and process it faster. To find the optimal number of components, I use this plot. So around the 20 components. So we have the lowest lowest error, and also we have the highest. It's not the highest, but it's like pretty much 95%, and we have the highest percent of the variance explained. So the 20 is the optimum value, and I used about 20 different algorithms, and these 2 algorithms, the ensemble back trees and QD work pretty well for both threshold and the Stalk residue. And the computer metrics, it shows the true moisture and the predicted moisture. So the diagonal of the matrix, it means we made a correct decision. So the predicted moisture was same as the true moisture, and the rest it shows the inaccuracies. So and the overall, when I show it in the percentile, you can understand it easier. And the overall accuracy is about over 90% in the bare soul, and the same thing for the residual Stalk. But we have higher inaccuracy, as I said, in the residual Stalk because of its structure. But still, as you can see, the total accuracy is over 85%. It's very good prediction power. And the last objective is we're gonna mount these 2 sets of the spectrometers on a stand. The 4-feet stand has UV, visible, and near infrared. We're gonna provide bigger sample compared to the objectives 2. So, and we put it in the under the ambient light condition. So we test it during the day. So we're gonna see if we can capture the moisture variability during the different ambient conditions. So in summary, in the first part, we instrument some portable spectrometers and integrate into the UAS for autonomous data collection. This part is almost done, so we just need to wrap up the programming part. And the second objective was the index. The index that we chose, it performed very well for the versal and poorly for the Stalk residue. And this part is done, and the paper is already accepted on this objective. And the third one is that we generate a model using machine learning algorithms for both lab and field data. So we did it for the lab data. And the last one is going to be the tested data acquisition system we got from the objective one, and to see if it works in the different ambient light conditions. And this is the project timeline I have. I'm pretty much here, and I finished the lab data collection, instrumentation, and UAS integration. So I need to finish the field data collection in about 2 months, and hopefully I'm gonna defend them next July or August. And I'm gonna thank my advisory committee, especially Dr. Sama. He's really helpful. I'm really lucky to work with him. Aaron Turner, Jason Walton, Surya Saket, Christopher Good, Luis Felipe for their help, and the whole GA departments for their support, and CloudMap research team. So this project is a part of their project, and it's funded by NSF. Thank you for your attention.
Any questions?
So what do I need to do to use this on my farm?
So to estimate the moisture?
Yeah, although I don't have irrigation system, but it'd be nice to know.
I guess it's doable. So the point is that actually the main part is that to generate a model. But when you are done with generating the model, so if you have a big data set and you have already most of the experiences you can have from a field or from a I don't know, from a soil type. So you can like make sure, so if you go to like a same kind of field, same soil type, and if you have your phone already, so it knows the variables, so the main part is like to generate a model. But when you're done with that, so I guess it's doable to have like an app and go to the field. That's what I think, but it should have some like sensors on your phone, but I'm not sure how easy it is.